know about multiplying, dividing, adding and subtracting rational problems, and we're going to apply it to some word problems. The word problems in the real world that rational problems look like, one of them is called involving work, okay? So if you're trying to estimate out your construction job, you would be using rational functions. So you have part of the work completed is equal to the rate of work times the time worked. And we're just going to look at a problem here that is just using this formula without any unknowns at this point. If it takes 5 hours to paint a room, what part of the room is completed after 3 hours? So if one room can be painted in 5 hours, then the rate of work is 1/5. It's your rooms per hour. So notice that you're going to take your time and put it 1 room over 5 hours. And the time so far that's worked is only 3 hours. Therefore, part of the work completed is equal to the rate of work times the time worked. So notice how you take the 1/5, multiply it by 3, and you get 3/5. So 3/5 of the work is completed after 3 hours. And that makes good sense. Now, where the word problems come in at is an example like this. If a painter can paint a room in 4 hours and her assistant can paint a room in 6 hours, how many hours will it take them to paint the room working together? Okay, and so what's going to happen here is we're going to let time be them working together, painting the room together, and that's key. The neat thing about the rational function word problems is setting up your table, okay? Notice we have the painter, we have the assistant, and then we break down the formula like rate of work, the time worked, and part of the work completed. So your painter has a rate of work of 1/4 because in 4 hours, she can paint the room. The time worked, we're not sure what it is, so we just put down the t, and so part of the work completed is t/4. Now notice the assistant is 6 hours, right, to paint this room. And so notice how part of the work completed, this is where our unknown is at, okay, t/4, t/6. So we go to set up this problem as the t/4 plus t/6 is equal to 1. Okay, and this 1 indicates the room. Notice that your LCM is 12, okay? And so what we're going to do is we're going to multiply 12 through each one of these, okay? So we're going to multiply the 12 through here. And by doing that, we can cancel our denominators, and then we get 3t plus 2t is equal to 12. We just add our t's together. 5t is equal to 12, and then divide. To find the t, just divide by 5, okay? So working together, it's only going to take them 2.4 hours. Here is another work problem. This time we have a sump pump, and it can pump water out of a basement in 12 hours. If we add a second pump, okay, the job is only going to take 6 2/3 hours. So how long would it take the second pump to do the job alone? And again, we're going to set up a table here. So we have time to pump 1 basement, and then the fraction of the job completed in 1 hour. So the first pump they told us was 12 hours. So the fraction of the job, and the second pump we don't know yet, but together they are 6 2/3. So, which is, by the way, 20/3 for your improper fraction. The fraction of the job for the first sump pump would just be 1/12. The second sump pump we don't know, so it's 1/x. So this is the rational part. Okay, and then we would place 1 over the improper fraction of 20/3. And so this is what our table would look like. Okay, so we're going to have 1/12 plus 1/x, and that's going to equal pumping out 1 basement, which is 20/3 hours. Okay, remember to flip your fraction here, and that's what the equation looks like. So we're looking at this and we have to find your LCD or also the LCM. And what's that going to be? That's right, the LCD is going to be 60x. And so we're going to come through here and we're going to multiply everything by 60x. Okay? And that means we're going to have 5x plus 60, and that's going to be equal to 9x. Now all we have to do is solve this equation, and what is going to be our x? Okay, so that's right. The x is going to be 15. So it's going to take 15, it would take 15 hours for the second pump. So that would be its rate. All right, another set of problems that we get to use when we solve when we want to do rational equations is our distant rate and time problems, okay? So like if you're driving a constant speed of 65 miles per hour, you travel for 2 hours, how far did you travel? Well, that's 65 miles per hour times the 2 hours, and that's going to be equal to 130 miles. So when we're doing these type of problems, there are 3 types of formulas we can use. Distance is equal to rate times time. Remember that time is equal to distance over rate, or rate is equal to distance over time, and these can show up in any of the problems. Let's take a look at this problem. We have a car travels 600 miles in the same time a motorcycle travels 450 miles. So if the car's speed is 15 miles per hour faster than the motorcycles, we have to find the speed of both vehicles. So again, we're going to set up a table. Now, the motorcycle, the rate is just x. They didn't give it to us. The car, though, is 15 miles an hour faster than the motorcycle, so that's x plus 15. Notice that our time, they just say the same time, and this is very important because we're going to use that in order to set up our problem. So when you see same time, your time is just an unknown. And then, of course, we have a distance of 450 and a distance of 600. Now, because we don't know the time, that's the formula we want to use. T is equal to distance over rate, okay? And so we have 450 over x, and we have 600 over x plus 15. Let's take a look at how this is going to set up. Because it's the same time, we got to set our equations equal to each other. All right? And then what's going to be our LCD? That's right, our LCD is going to be x and the x plus 15. Okay? And notice that we can cancel out the x, so we have 450 times the x plus 15, and then it's just 600 times x. You're going to have to distribute the 450 through, right? So at this point, we're just going to subtract the 450 from each side. So we get 450 times 15 is equal to 150x. Divide by 150, and so our x is going to be what? That's right, the x is going to be 45. So we know the motorcycle is 45, but what is the car speed? That's right, car speed is 60 miles per hour. So notice how that sets up, because it's at the same time, we can set our two parts of the equation equal to each other. Okay, let's take a look at this one. We have a boat. It can travel upstream. It's going to travel upstream 22 miles in the same amount of time. Again, same amount of time is here. It can travel 42 miles downstream. And then they tell us that the speed of the current is 5 miles per hour. And what is the speed of the boat? Well, we don't know what the speed of the boat is, but we're going to let it be x. And so when the boat travels upstream, it's going to be x minus the current because it's going against the current. But when it goes downstream, it's x plus 5 because that current is going to help it go downstream. Again, we have no idea about the times, but they are the same. Now the distance was 22 miles upstream and 42 miles downstream. Okay, so again, we're going to use the formula T equals D over R, and we're going to set these up using our distance over our rate. Alrighty, again, we get to set these equal to each other because, again, it's just the same time. All right, and our LCD is going to be what? That's right, it's going to be x minus 5 and x plus 5. Okay, So we'll multiply that on both sides. All right, notice that we get to do a lot of canceling. And so we'll have to distribute the 20 through the x plus 5 and the 42 through the x minus 5, okay? We're going to gather up like terms, so we're going to wind up with 320 is equal to 20x. And so what's our x going to be? That's right, our x is going to be 16, so the speed of the boat was 16 miles per hour. All right, here is a different type of an example. A salesman drives from home to a client's store 150 miles away. On the return trip, he drives 10 miles per hour slower and adds 1/2 hour in driving time. So what was the speed the salesperson driving on the way to the client's store? So we're going to have R be the rate of travel. Notice we set this up as trip to client and trip home. The distance is the same, right? 150. The rate to get there is R, so the time is 150 over R. Trip home, the distance is the same, but the rate now is R minus 10, okay? Now notice our times are not the same, but we were given it adds 1/2 hour in driving. So if we set this up, we can subtract the trip home from the trip going out, and that's going to give us 1/2 hour, okay? So then our LCM is the 2R. It's 2, the R, I mean, we don't get any breaks here. We've got to use all of those as our LCM, okay? And so we're going to multiply everything by the LCM, and we'll continue this over there. When we do that, when we do our distribution here, okay, notice we have to distribute the 300, we have to distribute the R, okay? And what happens is we get our R's are going to cancel, okay? And that means that in order to get a quadratic equation, we're just going to take the 3,000, subtract it, move it to the other side. Now then, we have to factor this. And once we factor this, we have to set each factor equal to, and we've done this before, each factor has to be set to 0. And I'm not going to do both of them. I'm just going to draw one out, okay? Notice that you get 60 and negative 50. Now the negative 50 is irrelevant. This is an extraneous solution. We can't use the negative 50. So the salesman drove from home to the client store at 60 miles per hour, which means he drove back at 50 miles per hour. So at 60 miles per hour, if we take the 150 divided by 60, the distance divided by your rate, we get 2.5 hours. The 50 miles, which is 10 hours slower, so that's 150 divided by 50, that gives us 3 hours. So the return trip took 1/2 hour longer, which is what we had set up in our original problem, that it was equal to 1/2 hour longer. And so that allows you to solve for the times and also the speed of how fast your client was driving. Alrighty, thank you for participating. Those are our examples of rational word functions. The end.